In this video, we're going to show how to prove most of the rules from differential calculus using the chain rule. More specifically, we're going to use implicit differentiation. Let's start with the exponential rule. Well, the basic exponential rule, the derivative with respect to x of e to the x equals e to the x, we're not going to prove using the chain rule. This rule is essentially true by definition. The way that we choose e is to be the number such that the exponential function f at x equals e to the x, which you see graphed here, has a tangent line at the point 0, 1 with slope 1. All equations of the form y equals a to the x for an a greater than 0 pass through this point, 0, 1. But y equals e to the x is the only one for which the tangent line at 0, 1 has slope 1. By making this choice, we essentially are stating that the derivative of e to the x equals e to the x. That might not be immediately obvious, but if we try to work it out, we can see why it's true. F prime, the derivative of f with respect to x, is equal to the limit as h goes to 0 of a difference quotient, which is e to the x plus h minus e to the x divided by h. If you factor out this e to the x, which doesn't depend on h, which is why we're able to take it out of the limit, then you're left with an e to the x outside of the limit times another difference quotient, which is e to the h minus 1 over h. But this is exactly f prime of 0, which we assumed was 1. So that means we have e to the x times 1, which is just e to the x. So the exponential rule is true essentially by definition. However, the exponential rule together with the chain rule is what we need to prove most of the other differentiation rules, as we'll see. We can start with the general exponential rule. For this rule, we want to prove that the derivative with respect to x of a to the x is equal to a to the x times the natural logarithm of x. So the standard way to do this is indeed to use the chain rule. So let's do it with the standard method first. And we just do it directly. The derivative with respect to x of a to the x, well, we start by rewriting a. The derivative with respect to x of a, we're going to rewrite as e to the ln of a. This is just using the cancellation laws, because e is the inverse of ln of a, so these would cancel out and just give you a. But now we have e to the ln of a raised to the x. So if you have an exponential raised to an exponent, you multiply the exponents together, and so you'll have the derivative with respect to x of e raised to the ln of a times x. And now we use the chain rule on this expression. This is the derivative of e to a thing, so this is going to be equal to e raised to that thing again, and then we multiply by the derivative with respect to x of whatever was in the exponent, which in this case is ln of a times x. Now the first thing here, e to the ln of a times x, that's just a to the x again. Remember, we started with a to the x and we rewrote it as e raised to the ln of a times x, but here that same expression is again e to the ln of a times x, so that's just a to the x. And over here we have the derivative of a constant times x. So the derivative of a constant times x with respect to x is just that constant again. So what do we have? We have a to the x times ln of a, which is exactly what we wanted to show. Now at the start I said that we were going to use implicit differentiation to prove these things, and we can do that here as well. So let's call this another method. And what we're going to start with is we're going to start by writing y equals a to the x. And our goal is to compute dy dx. So what we're going to do is we're going to start with this expression here, and we're just going to apply the natural logarithm to both sides. So we'll have ln of y is equal to ln of a to the x. And now we can use the properties of logarithms to take this x out of the exponent and put it in front of the logarithm. So we have that ln of y is equal to x times ln of a. And now we differentiate both sides. The derivative with respect to x of ln of y is equal to the derivative with respect to x of x times ln of a. The expression on the left, the derivative with respect to x of ln of y, well, the derivative of ln of a thing is 1 over that thing, times the derivative of whatever's inside there. But the derivative is dy dx, the thing that we're looking for. Now the derivative on the right is, again, we're back to looking at x times a constant. So the derivative of x times a constant is just that constant. So there's where we get our ln of a. So what do we have? We have that 1 over y times dy dx is equal to ln of a. And now we just multiply both sides by y. And then we have dy dx is equal to y times ln of a, but remember what y was. To start with, y was equal to a to the x. So dy dx is equal to a to the x times ln of a. Now this method is how we're going to approach the rest of the differentiation rules that we want to prove. We're going to recast everything as an implicit equation with some sort of y, and then we're going to compute dy dx using implicit differentiation. So, for example, the proof of the natural logarithm rule. Well, we already know what it is. The derivative with respect to x of ln of x is equal to 1 over x. But how are we going to prove it? We begin by letting y be equal to ln of x. And we want to compute the derivative of this y. So we don't know yet the derivative of the natural logarithm of x, but we do know the derivative of its inverse, which is the exponential with base e. So what we're going to do is convert this into an equation about exponentials and then differentiate that using implicit differentiation. So if y is equal to ln of x, that means that e to the y is equal to x. So now we differentiate both sides of this with respect to x. On the left we have the derivative with respect to x of e to the y, and on the right we have the derivative with respect to x of just x. Well, now we have the derivative of an exponential, and we know how to compute that. The derivative of e to a thing is e to that thing again, but now we have to multiply by the derivative of whatever was in the exponent. On the right, we just have the derivative of x with respect to x, so that's just 1. And now we're essentially finished, because we remind ourselves that this e to the y is just x. So this term right here is x. So we have x times dy dx is equal to 1, so we just simply divide by x. Dy dx is equal to 1 over x. And that was exactly what we claimed with the natural logarithm rule. We can do this same technique for inverse functions generally. So we want to compute, for example, the derivative of f inverse, where f is some arbitrary differentiable function. So we start by saying that y is equal to f inverse of x. This is the thing that we want to differentiate. So we recast this in terms of the original function f. If y is equal to f inverse of x, that means that f evaluated at y is equal to x. And now we simply differentiate both sides. So the derivative with respect to x of the left side, which is f at y, is equal to the derivative with respect to x of the right side, which is just x. Now on the left, we want to differentiate f at y with respect to x. Now in order for this to make sense, f has to be differentiable at y. Now y is equal to f inverse of x. Y is equal to f inverse of x, which is right here. So you can see that in the formula, we're saying that f must be differentiable at y, at this y. So this must be well defined. So in other words, we can compute the derivative. So it's the derivative of f at y, but we're computing the derivative with respect to x, so we have to use the chain rule. So the derivative of f is f prime at the inside function, but then we have to multiply that by the derivative of the inside function with respect to x. And this is equal to the derivative of x with respect to x, which is just 1. So now we just simply divide by f prime of y, and we'll have that dy dx is equal to 1 over f prime of y. But now we remind ourselves that y is equal to f inverse of x, so that tells us that dy dx is equal to 1 over f prime of y, but y is f inverse of x. And there's our rule for computing the derivative of an inverse function. We can use the same technique to prove the power rule. The standard technique for proving the power rule is to use the binomial formula, but that's a little awkward if your exponent isn't a positive integer. However, we can use the same technique to compute the derivative of x to the p, where in this case, p is any real number. So how's this going to work? We start with y equals x to the p, and then we just apply the natural logarithm to both sides. So ln of y is equal to ln of x to the p. And now we do the usual trick where we take the exponent outside of the logarithm and put it in front. So now we'll have that ln of y is equal to p times ln of x. And now we differentiate both sides with respect to x. So this will give us the derivative with respect to x of the natural logarithm of y is equal to the derivative with respect to x of p times ln of x. On the left, we have the derivative of a logarithm, of a natural logarithm, so that's going to be 1 over whatever was inside, times the derivative of whatever's inside, just using the chain rule. And this will equal p times the derivative with respect to x of ln of x. Remember that p is a constant. P is a constant, so we can just take it out. So now we have p times the derivative with respect to x of ln of x, but that's just 1 over x. So what do we have? We have 1 over y times dy dx is equal to p times 1 over x. And now the next thing to do is to multiply both sides by y. And so what will this give us? This will give us that dy dx is equal to y times p times 1 over x. But what was y? Y is equal to x to the p. So this y right here, that's x to the p. So we have that dy dx is equal to x to the p times 1 over x. Or if you prefer, dy dx is equal to p times x to the p over x. And now what do? We just reduce this expression right here. So x to the p over x, this is the same as x to the p minus 1. So we have that dy dx is equal to p times x to the p minus 1. So even if p is not a positive integer, we can still use the power rule to differentiate x to the p. We can even use this technique to prove the product rule. So we start once again by letting y equal the thing you want to differentiate. And we're going to apply a natural logarithm to both sides. So we have that ln of y is equal to the natural logarithm of f at x times g at x. But we recall the properties of the natural logarithm that convert a product into a sum. So this is equal to ln of f at x plus ln of g at x. And now what we want to do is we want to differentiate both sides. So we're going to have the derivative with respect to x of ln of y is equal to the derivative with respect to x of this term on the right, which is ln f at x plus ln of g at x. On the left, we have the derivative with respect to x of ln of a thing. So that's going to be 1 over that thing times the derivative of whatever that thing is, which is just dy dx. And on the right, we have the same sort of idea. We have the derivative of ln of a thing, so that's going to be 1 over that thing, which is f at x, times the derivative of that thing. But what is the derivative of f at x? It's f prime of x, plus the derivative of ln of a thing is 1 over that thing times the derivative of that thing, but the derivative of g at x is g prime at x. And now the next thing to do is to multiply by this y. So we're going to have that dy dx is equal to y times f prime of x over f at x plus g prime at x over g at x. But then we remind ourselves that y was f times g. So this is equal to f at x times g at x times f prime of x over f of x plus g prime at x over g at x. And now we just distribute, and we'll have that dy dx is equal to f at x times g at x times f prime at x over f at x plus f at x times g at x times g prime at x over g at x. And what do we have here? This f at x cancels with that f at x, and this g at x cancels with that g at x. And what do we have? We have that dy dx, the derivative of the product of f times g, is equal to the derivative of the first times the second plus the first times the derivative of the second. There we go, the product rule. We can actually do the proof of the quotient rule in essentially the same way. We start by letting y equal f at x over g at x, and then we apply the natural logarithm to both sides. That gives us ln of y is equal to ln of this quotient, f at x over g at x, which we can rewrite as ln of f at x minus ln of g at x. And that's really the whole reason to do this, because the logarithm turns the quotient into a difference. Okay, so now we differentiate both sides with respect to x, and this will equal the derivative with respect to x of ln of f at x minus ln of g at x, like so. The computations here are, at this point, essentially the same as the previous. On the left, we have the derivative of ln of y, so the derivative of ln of a thing is 1 over that thing times the derivative of whatever's inside there. And this will equal, again, we have the derivative of a difference, but it's logarithm of a thing minus logarithm of a thing. So the derivative of logarithm of a thing is 1 over that thing, which in this case is f at x, times f prime at x, minus the derivative of logarithm of a thing is 1 over that thing, which in this case is g at x, times the derivative, which is g prime at x. So notice that on the right you have the same thing, it's just that there's a minus here. So at the moment this is very similar, except there's just a minus. So the next step is to multiply both sides by that y. So we'll have that dy dx is equal to y times f prime of x over f at x minus g prime at x over g at x. But of course y, this y right here, is f divided by g. So if we just replace y with f divided by g, we'll have that dy dx is equal to f divided by g times all of this. So it's f prime at x over f at x minus g prime at x over g at x. And now we just distribute this f over g. We'll have that dy dx is equal to f at x times f prime at x over g at x times f at x minus, and now we'll have f at x, g prime at x divided by, and now we have a g at x times itself, so we have squared. And we'll notice that this f at x cancels with that f at x, and what are we left with? We're left with dy dx is equal to f prime at x over g at x. And I'm going to leave a little space there, and then I'm going to subtract from this f at x times g prime at x divided by g at x, quantity squared. So you might wonder why I left some space here. Here we have a g at x squared in this denominator, but here there's only a g at x. So if we want to give these a common denominator, then what we should do is multiply by a g at x over g at x. That will give a common denominator of g at x squared. But what does that do to our expression for dy dx? That gives us f prime at x times g at x minus f at x g prime at x divided by g at x quantity squared. That is to say, the derivative of the top times the bottom minus the top times the derivative of the bottom divided by the bottom squared. And yes, that is the quotient rule. So there's one other derivative rule that I want to talk about, which is the cosine rule. Now this one is a little bit different. I'm not going to show this one using logarithmic differentiation like I have the others. The whole point of this exercise is to explain why there's a minus sign in front of the sign here. The derivative of sine is cosine, but the derivative of cosine is the opposite of sine. And in fact, all of the co-trigonometric functions, if you differentiate them, will give you a minus sign. And where does that minus sign come from? It comes from the following identity. So cosine of x is equal to sine of pi over 2 minus x. Now, in fact, this is historically the definition of cosine, because if you start with this angle x, then what is pi over 2 minus x? Pi over 2 is a 90-degree angle minus the angle x, if you think of this x as an angle. So if we imagine these as being parts of a triangle, so here, if this is a right angle, and this is the angle x here, then this angle right here is pi over 2 minus x. So this is the complementary angle in a right triangle. So cosine of x is sine of the complementary angle, and that's where the CO comes from. Cosine, sine of the complementary angle. So this in fact is the historical definition of cosine. But notice exactly what's going on here. Now if we differentiate with respect to x, this cosine term, that's the same as the derivative with respect to x of sine of pi over 2 minus x. But now it's the derivative of a sine. So if we know the derivative of a sine, then we can say, okay, well the derivative of sine of a thing is cosine of that same thing, pi over 2 minus x. But now we have to multiply by the derivative with respect to x of whatever's inside there, which is pi over 2 minus x. The derivative of pi over 2 minus x, that's equal to -1. And that's where the minus sign comes from, because here we have cosine of pi over 2 minus x, which is the sine of the complementary angle. So that's just sine of x in this case. So what do we have? We have that the derivative of cosine of x is sine of x times the -1, which is the opposite of sine of x. And that's why there's a minus sign there. And in fact, that's true for all of the trigonometric functions that start with a co. They're the trigonometric function evaluated at a complementary angle. And so you have these similar identities. And it's the derivative of this pi over 2 minus x term that gives you the -1.